So I really recommend watching these videos between now and the test because I'm pulling the same drill with the other class, and it's highly unlikely we'll do the same one. So it would be worth your time to look at both. All right, so let me pull up my screen here, or I'm going to call it on my iPad so I can actually write legibly. But in the meantime, what should we do to get started on number 14?
We're aiming for undoing the chain rule, I'm guessing, because it's two different functions with different powers. So
okay, so yeah, undoing the chain rule is one of those things. If you can make it work, then that's one of the easier things you can do. In this case, can we go to the chain rule right away?
No.
No. Okay. I'll kind of spoil it for you a little bit because this might be a little bit of me jumping the gun on what he's going to do on Wednesday, because I think this is something he was going to practice in more detail with you. So remind me, what is the function we're integrating here? Is it secant to the 7th or something like that?
secant 7x times tangent cubed x.
Tangent cubed x, okay. So since somebody mentioned it, we said, all right, we want to undo the chain rule. So that is eventually what we're going to do. But right now, let's just talk about which direction would you go. Like, if you're saying undoing the chain rule, then you're telling me that the derivative of something here is related to, basically the derivative of one of these things is one of these other things. So which direction are we going with that?
Derivative of tangent is secant squared.
Okay, and I have in the chat from Min2, don't you have to use trig identities? You are exactly right. So I know the derivative of the tangent of x is equal to secant squared of x. So based on what Ben just told me and what Min2 put in chat, we're gonna have to use those things together to make this integral possible. So I know the derivative of tangent is equal to secant squared. Right now I have tangent to the 3rd power. So it'd be really great if I could get tangent to just be to the 1st power. So since Min2 offered up the advice of using a trig identity, what would be a useful one here?
Derivative of secant x.
What's the derivative of secant x?
Secant x times tangent of x.
So I think we're gonna have the same problem there. We have our tangent function is still cubed.
Can we just do our tangent to the 4th?
I'm sorry, what was that?
Can we just do our tangent to the power of 4?
How would we do that?
Just do it. I mean, I'm just guessing. I'm sorry.
No, we're not going to be able to get to tangent of the 4th in the integrand here. So one thing, and like I said, we're jumping the gun a little bit. So maybe you haven't. Never mind. Min2 just told us the one we want. I'm actually going to build up to. If you're seeing what Min2 is putting in the chat there, I'm going to build up to that a little bit, because there are these things in trig called the Pythagorean identities. And there's a primary one, and then there are two that are more kind of based on that as a consequence. But you have probably seen this. Nope, not cosine again. Cosine squared of x plus sine of squared x equals 1. And I'm hoping and I'm confident that most of you remember that. Like, it's one of the things that you've hopefully committed to memory over the last few years. But from that, we can use this thing to build up a couple others. So I'm going to divide every term by cosine squared of x. And from there, I get 1 plus, what is sine squared over cosine squared?
Tangent squared?
Tangent squared. And 1 over cosine squared?
Secant squared.
Secant squared of x. And then one more move I'll do here. tangent squared of x equals secant squared of x minus 1. So here's the real power of these Pythagorean identities when you're trying to do these integrals that are involving trig functions. You can basically trade powers of 2 of some trig function for another one. So because of that, I can get my tangent cubed down to tangent to the power of 1. Because what I'm going to do is this, and I'll break this down in steps. And now that I have that, I can do secant to the 7th of x times secant squared of x minus 1 times tangent of x dx. So then I have secant to the 9th of x minus secant to the 7th of x tangent of x dx. How are we feeling?
It's not getting us where we're going, but a really simple rewrite of that identity would get us there.
What do you mean by that, Ben? How would we rewrite?
Instead of tangent squared x equals secant squared x minus 1, we want the secant squared x equals, I always try to screw myself when I try to do these in my head, but that's
Trying to solve for secant squared
yeah,
x.
secant squared x is yes.
Okay. So a couple options here. Yes, we can use secant squared of x, but then what we're going to have is a situation where we're going to have to do this to the secant to the 7th 3 times, and we're just going to get a nastier integrand. So I would like to focus on, I believe Matthew gave us this one. The derivative of secant is secant tangent, right? So I'm going to pull one of these secants out and do this. I'm going to have secant to the 8th of x minus secant to the 6th of x times secant x tangent x dx. And just to make this look a little simpler, and this is one thing, I've gotten a couple of questions in the last couple of days about this. When you have things added or subtracted, you can pretty easily break those apart into separate integrals. This is one of those things that it comes really into play when you're dealing with fractions. I forgot my other secant, didn't I? Yep. So now let's just look at one of these. So let's look at the first one. It says secant to the 8th of x times secant of x times tangent of x dx. Can we use undoing the chain rule with that?
Before you get there, you lost me on how you were able to just add those two together unless you distributed the.
Yeah, so basically, let me go ahead and drop in the step that I see.
Oh, you distributed the two of them. Okay, I see. You distributed the secant x tangent x against the.
Yeah.
Okay.
So while I'm writing this down, can we now use undoing the chain rule of my final step down there to get to the integral I want? So let's remind ourselves of what the chain rule looks like. So chain rule is used to differentiate composite functions. And when I differentiate, I get f prime of g of x, g prime of x. So if I'm undoing the chain rule, I want to go the opposite direction, which means I would really like to have, is there an inner function whose derivative is there? And do I have the derivative of that, or do I have that outer function present? So hopefully you see that we have secant of x there, and we have its derivative. So let's try to build these things up here. Let me say that f of x is equal to x to the sixth. If that's true, then really what function am I nesting inside x to the sixth to get what I have here?
Secant.
Right. Secant of x. Oh, that's not right. Secant to the sixth of x. And that all comes from the fact that g of x is equal to secant x. And like we already said from Matthew a while ago, g prime of x is equal to secant x tangent x. So one thing I'll say about, undoing the chain rule is pretty simple, but it does still require some organization to make sure that you have all the pieces in place. So in this case,
Excuse me?
Yep.
How do you go from secant 8 of x to secant 6 of x in the last part?
let me bring this down to make clear. I'm not saying those are equal. Because those are two separate integrals. I'm not saying they're equal. Is that what you were asking, Mark?
Yeah. I
Okay.
just look at it because it looks really honestly, like the work looks really messy, kind of. Not necessarily
Yeah.
messy, but looks like a mouthful, if you will.
Oh yeah, absolutely. And honestly, there's not really a way around it. I will tell you, this could have gotten even messier if we had decided to break secant down to the power of 1. I think you'd have 5 terms to deal with. So now that we have this,
Yeah, Steve.
yeah, go ahead.
Where did you get x to the sixth for f prime?
I will say this. This right here is basically focusing on this integral. So if you're trying to match that x to the sixth with that left-hand side, then yeah, that doesn't fit. In fact, let me do this before I really answer the question you asked. In this case over here, f prime of x would be x to the 8th.
It's the same thing. We've got just 6 on the right and 8 on the left, right?
Yep. F prime of g of x is going to be, I should call this f prime. Secant to the 8th of x. And same thing here, g prime of x is equal to secant x tangent x. So, and then Nicholas is asking, from here we just do the chain rule. Yeah, I mean, everything we've been doing so far has been building up to this idea of using the chain rule. And just to point out, which we've been dealing with it the whole time, we had to use a trig identity to even get this far, or to even facilitate this process. But yes, now we can use the chain rule, because now what I have here is this. This guy is f prime of g of x. And this guy right here is g prime of x. And if you look at over here, how do I take the chain rule and take an antiderivative with it? That's going to leave me with f of g of x. And in this case, what would f of g? So how do I get from f prime of g of x to f of g of x?
You take the antiderivative,
Yep. The antiderivative of what specifically?
f prime with the inside function g of x.
Okay, so what is the antiderivative of x to the 8th?
X 1/9 x to the 9th.
Right, so I want 1/9 something to the 9th. And in this case, I still have to evaluate that inner function. So it'll be secant x. And then hopefully that'll clue you in on what's this other antiderivative going to be.
1/7 secant x to the 7th.
And then I'll just clean this up and make it look like. There you go. So, like I said, I mean, I think this is something that Mark was going to spend a large chunk of the day on tomorrow. So it'd be nice to have a little bit of a head start going into it. But yeah, using trig identities to get to the integral is really the that's step one. Any more questions about this one before I move on? Actually, I got some stuff in the chat. What's going on? Approximately how many antiderivative problems will there be? Don't happen to know off the top of my head, but I can promise you it'll be quite a few. And these are the kind of things that, you know, basically, you know, hopefully you all looked at the email and the file I sent out yesterday with that partial fractions example. But really, with a lot of these, very little of finding the antiderivative has to do with calculus. A lot of it has to do with choosing the right method and, you know, organizing and making doing all the things correctly that you need to do algebraically. And that just comes with practice. So if you haven't worked through a bunch of those antiderivative ones in that PDF, I would definitely do that over the next few evenings. And just to make sure that, you know, if you see something like this, which you may or may not, yeah, if you can do it in 2 minutes instead of 6, then that obviously gives you a huge leg up. Any more questions? What number was this, by the way? 14?
Yep.
Yeah.
So I'll share this file out when we're done. What else do you want to look at from that PDF? Let's go away from trig stuff for now. Get a good variety.
I have a question, but it's not on one of like the files. It's on one of the iMath. Yes, can I ask
Sure, let's do
about
that.
So I got one of the problems. It was the integral of e to the x divided by 6ex plus 6
Okay, let me.
dx.
So e to the x
Divided
over.
by 6ex plus 6.
Okay, this is a good one to talk about because this is I've gotten a lot of questions like this recently. All right, so what's the first method we kind of look at?
Undoing chain rule.
Undoing chain rule. Can that be done here?
No.
I hear a vote for no. Anybody else?
For me, it looks almost
Yes.
like decomposing a fraction.
Right, but keep in mind that decomposing fractions, and maybe this kind of got lost in the details, but decomposing fractions is a good method for polynomials or rational functions. Not really a good, it's not really going to make a dent in this. So I heard somebody say yes to chain rule. How would that happen?
So, well, the derivative of e to the x is going to be e to the x. So if we assume it's like the, what's it called? The f prime of x, or the f of x is like 1 over x.
Okay,
right?
So let's call f of x 1 over x.
And then g prime of x would be e to the x.
So g prime of x would equal e to the x.
And then g of x would just be the denominator.
And then g of x would be equal to what?
The denominator.
The denominator. And that's, let's see if that'll work. One thing just to, all right, so you have g of x equals 6 e to the x plus 6, g prime of x. I don't think our g prime of x is really e to the x, but it's close, right?
Yeah, I think I have to do something with the is it coefficient? Yeah, the 6.
Yeah. So what is the derivative of 6 e to the x plus 6?
6 e to the x.
Right. All right. So I think basically let's build this up based on our like building blocks here. We have g of x, right? Or really what we have is, we have f of g of x, right? Because we have 6 e to the x plus 6 contained in the x of 1 over x, right?
Mm-hmm.
So we do have f of g of x. Do we have g prime of x?
Almost. Because of the numerator.
Okay. So, well, it's not exactly the same, right? But is it still okay to use for undoing the chain rule?
I think so. We just have to like modify the finished product of the chain rule.
Yeah. So one thing I will do is this. So, and I don't think Mark really does this method, but I think it might help some of you. If I know that g prime of x is equal to 6 e to the x, what I really want is e to the x, right? So that means e to the x is equal to 1/6 g prime of x. We okay with that? I don't think Mark really does this like that, but are we okay with why I did that?
I'm cool with it.
Okay, so basically what I have now is f of g of x times 1/6 of g prime of x. So now, hopefully you're seeing that, yes, absolutely, I can do chain rule here. Because what I have is really f prime of g of x times g prime of x. And now that we have all those pieces in place, you should be able to tell me what the antiderivative is.
If I'm doing this right, it's 1/6 the natural log of x, or natural log of 6 e to the x plus 6.
Yes.
Also, Mark just dropped a question in chat.
Yeah, see that. All right, and then really don't need that, I guess. Okay. How do we feel about that? And then not necessarily going to do it here because I trust that you will do it, but we're still all in that phase, myself included, where derivatives just feel more comfortable than antiderivatives. So, I mean, I think it's definitely worth the time on the test on Friday to take a derivative of this and make sure that you get back to where you really started.
I have a quick question.
Yeah, I think I got I got a couple of questions in chat that I want to address. Somebody is asking, will I lose points by just doing integration by parts? Integration by parts is really the same thing as undoing the product rule. So no, you won't lose points. That's basically what you're doing. I think Mark just he just frames things in a different way, but really, if you compare, how Mark uses how Mark undoes the product rule with that template you use for integration by parts, they're identical. So yeah, that's fine. And then did somebody say they had a question? Was that you, Ramon?
Yeah, that was me. I just want to know, just when should I be using the absolute value for natural logs?
Really, so I'll answer that a couple ways. The short answer, the easy answer is always.
Yeah, that's what I assumed.
Yeah, but in this case, 6 e to the x. E to the x can never, ever be negative. It can never be 0. So this is one of those cases where I'm okay not to do it, but really, yeah, if you want to be totally safe, absolute value always. Matthew asks, where did the 1 over x come from for f of x? Can I pass that off to somebody? Where did the 1 over x come from?
I can take it.
You've got the 6e to the x plus 6 in the denominator. So
Right.
the x in that is that whole 6e to the x plus 6.
Right. So yeah, that's exactly right. And with composing functions, if I give you a function, you can come up with a composite function an infinite number of ways, but not all of them are going to be useful, especially when you're trying to take an antiderivative. So I think this was the way to go. And then I thought I saw another. Hannah's
Yeah, I
asking.
need help with some.
Yeah, I know. I'm answering the quick questions in the chat. Can you do this problem with integration by parts? The short answer is you can do any integral by integration by parts. All right, Mark, you're up. What do you want to talk about?
Yeah, I have another question with iMath.AS. I probably am overlooking it way too much, but I need help with tangent for tan 4 of 9 of x.
Tangent of 49x?
No, tangent to the power of 4, 9x.
Oh, okay, I got you. All right, so I'm not going to finish this one because this is quite a bit like one we just did, but how would we attack this?
I was actually thinking use one of the trigonometric identities. I tried doing tangent squared of 9 of x squared.
So you squared this? Oh, I see what you're saying. Okay. So basically you have tangent squared of 9 of x squared.
Yes.
All right. And then where can you go with that?
I can use the secant squared of x minus 1 rule. Minus 1, yep. All squared dx.
Mm-hmm.
I tried distributing the square, but I don't think it actually works.
Okay, so if you expand this out, what should happen is secant to the 4th of x, 9x.
Yeah.
Minus 2 secant squared 9x.
Wait, how do you get minus 2 secant squared 9x?
So if you were to FOIL this out, you would get minus secant squared minus secant squared.
Okay, so you did FOIL. Okay.
Yeah, I am doing that. So plus 1 dx.
I could be mistaken, but couldn't we just undo the chain rule? Because isn't tan to the 4 the same as tan 9x to the 4?
Oh yeah, that's why I'm hitting a dead end. Yeah, this is absolutely a lot easier than I was trying to make it. So in fact, when you get here, I can anti-differentiate that and that, but then this is going to be the same problem. But let's talk about undoing the chain rule, and I totally blew it because I didn't even think about it, which you always should because it's one of the simplest things you can do. But yeah, what is the derivative of the inner function there?
Tangent of 9x?
Well, the inner function, I would call it 9x.
Oh,
So
so
the
it's
derivative
9.
would be 9. So yeah, you do have a constant. You do have a constant multiple of 9, so you can use that. So I'm not going to erase this to hide my shame, but really what you can do is, yeah, this ends up being 1/5 to the tangent of 5th 9x. Right?
That makes sense.
I don't think I'm totally done though.
Yeah.
Divide by 9. Divide by 9.
There you go.
Yeah.
All right. So yeah, my advice would be just always think about the chain rule, even if it's not going to work, because you're only going to spend a couple of hopefully no more than a few seconds seeing that it's not going to happen. One question I got from Franco that I really want to bring up, and I'll just give you a quick counterexample, Would all fraction problems have a derivative with natural log? Short answer is no. Because what about this? So that, hopefully you see that that will not give you a natural log. That's going to give you, that's just simple power rule. Jillian is pointing out that the arctangent shows up a lot. So if the iMath hasn't like made you go review it, and if you don't remember it, one thing to pay attention to is this, the derivative of arctangent of x, which is what?
One over x squared plus 1.
So if you see, and going the opposite way, if you see that integrand, and I never want to guarantee you anything, but I would expect that to show up at least once.
And it doesn't have to be 1 in the numerator and denominator. You can factor those out in order to get
Yeah.
to that.
I mean,
Which
for example,
for the loop.
if I have 12 over x squared plus 1,
You can just pull the 12 out and then
right.
and then you've got.
So one thing I want to point out with taking antiderivatives is if you have a multiplied constant, you can always pull it outside of the integral if it's easier for you to think about.
And that cleared up one of them by pulling a fraction out. I
Yeah.
wound up with, 1/87th or something weird like that.
Yep. And there's at least one problem in the iMath where it gives you some strange coefficient, like some 3-digit coefficient that yeah, it absolutely would be easier to think about if you just pulled it out to the side and dealt with it only when you had to. All right, what else should we look at?
I have a quick question.
Go ahead.
Do you know of any like good resources for like proving these derivatives and stuff? Because I always feel like seeing the proofs and stuff just kind of helps me comprehend and memorize it a bit more.
I think a good key phrase to use is first principles. So like if you want to do derivative of natural log of x by first principles, then instead of just showing it to you, it will actually develop it for you. All right, Michael has a vote for number 3 on the review sheet. And partial fractions are always good to look at. And like I said in that file I sent out, I mean, 95% of this integral has nothing to do with calculus. It's all about the algebra that gets you there. All right, so 3x plus 5 over 5x squared minus 4x minus 1 dx. All right, so how do I get started?
You find you kind of foil out the 5x squared minus 4x minus 1. Not foil out, but what's
go backwards. What's the So factor is the word you're looking for.
That's my bad. That's the one.
You're good. All right, anybody know how this thing factors?
Yeah, it's a 5x plus 1 x minus 1.
5x plus 1 x minus 1. 5x squared plus x minus 5. Yep, I agree. All right, that's good. In fact, you know what? I'm not even going to carry the integral for now, because we're not integrating anything for quite a bit. What else? What now?
So now we do the partial functions.
Okay. So what's that decomposition going to look like for this one?
A over 5x plus 1 plus b over x minus 1.
Okay. So yeah, this is that case. I mean, there are no special cases to worry about here. So yeah, this is good. Now from here, what do you want to do?
You get a common denominator?
Well, you kind of already have that.
It looks like cross multiplying, but it actually
Yeah.
isn't.
So that's one of the reasons I wanted to send out that email, because yes, it looks like cross multiplication, but really, and in this case, it's going to look that way the whole time, but that's really a coincidence. What you're really doing is I am multiplying both of these by whatever will clear all the fractions out. So in this case, I'm multiplying both sides by 5x plus 1, x minus 1. So what is that going to do on this left-hand side of the equal sign? It's going to make everything go away. What's it going to do on each one of these terms? Well, for this a, the 5x plus 1 is going to cancel, and I'm left with x minus 1. Opposite story for the b fraction. So now if I clean that up, I get 3x plus 5 equals a times x minus 1 plus b times 5x plus 1. We good so far?
Now we just distribute.
Yeah, also right-hand side, we distribute all the brackets. Ax minus a plus 5bx plus 5. Good?
5bx plus b.
That's what I said.
Of course it is.
Now what?
Now we kind of rearrange it so that the x terms and the no x terms are kind of their own equations.
Yeah, so I'll break this down kind of slowly, because I feel like this is where I heard a lot, and I saw a lot of questions about this yesterday. So first I'll just move everything around. So ax plus 5bx minus a plus b. And I'll really make it obvious that these things are so now from there, I know this. I know ax plus 5bx is equal to 3x. And I know that negative a plus b is equal to 5. So from there, I can just, knowing that the coefficients have to match up, I can just leave off the x. And it kind of looks like you got a favor done to you here.
Oh yeah, because we could just add them.
Yep, adding them straight down, you get 6b equals 8, which means b equals 4/3. Which means a equals, I don't want to set a bad example, it's actually working through. Negative a plus 4/3 equals 5. Negative a equals 5 minus 4/3, which is equal to
4/3 minus 5.
Yeah. So a is equal to negative 11/3. All right, are we good with how we got a and b? So now I am going to go to the actual integral of this. And this is going to look bad, but I think it's actually easier to do it like this to make it easier to think about what the antiderivatives are. It's probably more mathematically clean and accurate to put the 4 in the numerator and the 3 in the denominator, but I think this really helps out with getting to the antiderivative.
I totally agree with that.
All right, so now we can just handle these one at a time. So what is the antiderivative of that left term?
Actually, looking at this, I would simplify it first by pulling out a 1/3.
Okay. Oh yeah, that's a good idea. So this equals 1/3 times the integral of negative 11, and that's a great idea.
Would
All right.
they both just be undoing the chain rule? Because it looks like another 1/x situation.
Yeah, and this is undoing the chain rule, but it's hopefully it looks a little more simple to you than our last experience with this did. So we have a linear denominator and a constant numerator. True or false? Linear denominator, constant numerator means natural log. All the time.
Typically, yes, maybe not all the time, but often. I could see 1 over x squared plus 1 as being an exception.
I said linear denominator.
Linear.
So in that case, yes, it absolutely is always gonna be natural log. Because basically you have some function in the denominator and its derivative in the numerator. And that yields a natural log. So what would the antiderivative be of negative 11 over 5x plus 1?
Negative 11 over 5 natural log 5x plus 1, or the absolute value of 5x plus 1.
Absolutely. There you go. And then the term on the right.
Just 4 ln x minus 1.
Yep. And then I'll reincorporate that 1/3 over there. So I get negative 11 over 15. Natural log of 5x plus 1 plus 4/3. Natural log of x minus 1 plus c. All right. Any questions about this?
I have a question.
Yeah.
So you said a linear denominator means its antiderivative is always the natural log?
Linear denominator and constant numerator.
Okay.
Yeah. So yeah, both of those things have to be true.
Okay, thank you.
No problem.
If you've got an x on top, you can't.
Right. All right. So I got a couple of question here from D that I really want to bring up because I think it's important. So, you know, we're not going to do this one because I'm not even sure if it'll work. But let's say I have something like 3x plus 2 over, you know, something you can't factor like x squared plus 4. I guess that wouldn't make sense because then you can't break it down. So x times x plus 4, x squared plus 4. Then what would the skeleton of this thing look like? Actually, I really want to, let's make this more complicated because got a lot of special cases to think about. What would the partial fraction decomposition look like for this guy?
Is this going to work because you've got the same degree top and bottom?
I do not have the same degree top and bottom, so that's one thing I wanted to point out as well. What is the degree of the numerator?
Oh.
2,
And what's the degree of the denominator?
4.
4. So yeah, the degree comes from what happens if the greatest power of x when you expand everything. So D says ax plus b over x squared plus cx plus d over x squared plus 4. I agree with this. I do not agree with this. At least, I think we can break down the one on the left even more.
Don't you need on the bottom x plus x squared? Like on two different things, it's like a over x plus b over x squared.
Yep. And back to D's other question. You know, if you have a quadratic denominator like we do here, why does the numerator have to be linear? Why can't it just be constant? So here's the thing with partial fractions, and I think Mark said this right when he started developing this, and maybe he hasn't brought it up since, but when you're doing this, the goal is to get to a place where you have, you know, a lot of linear functions where the denominator is the degree of the denominator is larger than the degree of the numerator. So those are kind of things you have. But when you have a denominator like x squared plus 4, what's the degree of x squared plus 4?
2.
2. Which means I want the degree of the numerator to be less. But I don't know how much less it could be. If you assume that the degree is 0, that's when you would have that constant there. But all you know is that the degree is going to be less. You don't know if it's going to be, strictly 0. So we might work this through and find out that C equals 0, but we can't do that.
And looking at that, the first line where you didn't like the AX plus B, wouldn't that be okay if you took that approach? Because if you did break that up, you've still got AX over X squared.
Oh yeah. Oh yeah, and that's exactly right. So yeah, if you were to break that down, then yeah, that would come out to A over X plus B over X squared. But still, I mean, your goal with this partial fraction decomposition, I want to break this into as many small pieces as I can. Franco asked, why did you split the X squared into X and X squared and repeat the X squared? So one thing I should point out here is, if I have this common denominator, let's do this, 5 over X squared plus 3 over X squared plus 4. What is the common denominator between these two fractions?
It's what we started with.
Right. It is so, and one thing I need to point out, and I feel like this is a hang up for a lot of people, it is not simply X squared plus 4. It is the combination, that multiplied combination of X squared times X squared plus 4. So the fact that I have X squared here and X squared here, those things aren't really, you can't make a common denominator in the way that you expect there by just, absorbing 1x squared into X squared plus 4. Also, I'm going to take Franco's other question and put it to the room here. Why do I have to have this term and this term?
Is it so you can accommodate for all possible denominators?
Right. So let's say, I have no idea what smaller fractions have to be added together to get this. So if I assume it's just, something over X squared plus some linear thing over X squared plus 4, you might start solving that and realize that there is no combination of A, B, and C that actually gets you back to this. So yeah, it's just a matter of you have to account for every power. Like for example, I know this is going to be a little simpler, but if let's say I had 7/12, sure, there's a way to break that down into something over 3 plus something over 4. But maybe I added something over 2 and something over 6. So it's just a matter of you got to take into account every single thing you can think of that might have contributed to that original function you're trying to integrate. All right, I'm going to go ahead and stop the recording. We have hit 12:50.